our last talk. My big pleasure to introduce Prof. Chenyang Xu from Princeton University, and Chenyang will speak about discreteness of local volumes.
Thank you very much. First, I want to thank organizers for inviting me to give the lecture. It's my second time to visit Newton Institute. The first time was 2012. It was one of my first time to mix with complex geometers. And I still remember during the conference, there was a newly announced result then, given by Simon Donaldson, talking about his joint work with Song Sun. So basically, the result is just say that if I have an X Fano, if I have a sequence of them, then after passing through subsequence, you take the Gromov-Hausdorff limit. Then you get another Fano variety. Which also has a Einstein metric. So I think the paper is called the Gromov-Hausdorff limits of Kähler manifolds and algebraic geometry. And then later they wrote another paper called the Gromov-Hausdorff limit of Kähler manifold and algebraic geometry too. And it's concentrated on study this part. So this is not necessarily a Fano manifold. I mean, this part is Fano manifold to start with, but this part is only a Fano varieties. So in particular, you may have a singularities there. So if I have a singularity, then I still have this metric. Then I can room in and to study the Gromov-Hausdorff limit of so-called tangent cone. Then they prove that the limit is another algebraic singularity with Calabi-Yau flat cone metric. And let me just denote it by Y with kind of cone metric. So somehow I would say to understand this process in algebraic geometry is, I think, one of the most interesting problems in the business of K-stability, because on one side, I mean, this construction, this Gromov-Hausdorff limit construction, is a very analytic construction. I mean, somehow it's a metric. I mean, it's very hard to tell algebraically what it is. On the other hand, if you just look at what's happening, it's completely algebraic, right? You have a sequence of Fano varieties. There is a limit, and you have a singularity. There is a limit. So geometrically, there should be some algebraic way to understand it. And by now, we know that this limit is basically the reflection of the fact that the K-modular space is compact. But even with that knowledge, we don't have a very direct construction here. However, for this limit, for the second one, for this local picture, actually, to understand how to construct the algebraic, at least conjecturally, that was earlier. So first, I mean, in their second paper, they posed such a conjecture that the Y, I mean, this singularity, if you forget the metric, it only depends on the algebraic structure. So here I forget the metric, I just remember the singularity as algebraically. And this conjecture was answered a while ago by Qi, Xiao Wei, and myself. And of course, the answer is yes. And but during this understanding, it was actually based on some like a more general construction by Qi. So it's called normalized volume. So So here, I mean, the conjecture was posted for singularity, which appear on some Gromov-Hausdorff limit. But you can just study singularity as it is, completely forget the metric, so it doesn't have to have any global geometry. So the main character here is we study KOT singularity. So this is completely general for any KOT singularity. And Chile defined the normalized volume for valuation V. So V here is some valuation centered at this point. So some people call it like a non-Archimedean link. So this was defined. I mean, yesterday you already said the definition, so I'm not going to repeat it, all the details, but let me just say that this is defined to be the volume times ax v power to n, and this is infinity if the I write it this way because a priori, I mean, this volume could be zero. But this formula will actually imply that when this happens to be the volume of the valuation zero, the logarithm has to be infinity. But anyway, as the series goes by, we will say that we actually don't necessarily, we don't have to worry about those kind of like bizarre valuations. All the valuations are kind of geometric. So then we define the local volume of the singularity. Actually, it was called the normalized volume in some of the talks, but I think a few years ago we agreed to just call it the local volume. So this is the infimum of all the V as above of the. So then the question, I mean, I'll explain a little bit later why we are interested in this normalized volume, how it relates to the Donaldson type question. But here I will pose the first question is, so if I consider this set, this is just all the normalized volume. Let me just write in this way, such that the dimension x is fixed. Then what this set will look like. And we already know some fact of this set. For instance, yesterday we heard that the largest number of this one, the largest number in this set is n power to n, is given by the smooth point. And conjecturally, the second largest one is given by the rational double point, which is 2 minus 1 power to n. But that's not known, I mean, for dimension larger than 3. And for quotient singularity, you say that the n power to n divided by some integer appear. So, but I want to get more general information about this. So in general, it's pretty hard actually to compute a given singularity. What is the normalized volume? For instance, for three-dimensional terminal singularities, that's not known at all. But the first result, which I proved with Ziquan, I think 2 years ago, is that the only has algebraic numbers. So all the numbers here are algebraic. Actually, when Donaldson wrote their paper, they already proved that the singularity appear in their setting are only algebraic numbers. Because we can basically prove for any KOT singularities, some kind of geometrical thing will happen, which I'm going to explain. Then that will imply all this, for all KOT singularities, the numbers will be algebraic. And so today I want to concentrate on another result, which for this year is that if I look at this set, it only has accumulation point 0. So in other words, if you fix a positive number, you look at the volume larger than that, it's always discrete. There are only flat many of them. So the proof of the second statement, there are two steps. So the first step was understood before. That's called a stable degeneration. It used to be called a stable degeneration conjecture, but now it's theorem. So what's this? So there are several parts of this theorem. So I only want to talk about some 2 or 3 parts of the theorem. This was originally given by a series of conjectures by Chile and myself, but now everything is proved. So first let me just start to define some notions. So I consider a K-OT singularity which is given by spec R, so some algebraic ring. And I consider there is a torus action on this. So this some torus. And I assume this action is good. So you think about there is only one fixed point. So and if I write this ring, I decompose it according to the weight. M is basically the weight. Then particularly I know R0 is just the base field, because I assume the fixed point is, so let me just say this is a good action. So basically you just know there is a one fixed point. And so I define the Rib cone, which is all the vector in the dual of this M. But now I consider all the real vectors. So originally it's only a lattice, but now so this I divided as so not. And I require that the pairing of C together with alpha is always positive for any alpha not equal to 0 and alpha is not equal to 0. So particularly you say that for such C, I can define a weight valuation C, which is non-trivial because C is not 0. And so that if I have a F in R, I just define the C, the value of this weight C on alpha to be the minimum of the pairing of C with alpha, such that the alpha is not, sorry, if I write F to be sigma of F alpha, and F alpha is not equal to 0. So I can get such valuation. And so then I say that the X together with this prefixed vector is, so first I call this kind of data to be Fano cone. Here I require that this R to be K-OT. So let me just to say, of course you can consider more general T action singularity, but in my talk, I only consider the K-OT singularity one. So X together with one such C is called the Fano cone. And I would say this one is K-semistable. But I defined, if I don't leave, that the volume of this singularity defined that way as a minimum is actually computed by the valuation given by this C. So this was not the original definition of K-semistable cone. The original one was given by Gabor-Siglidi and Tristan Collins. They studied by using test conflation. I mean, this more traditional way of defining it, but Chenyang and I proved that this is equivalent to the original one. So then the theorem, the stable degeneration theorem, which I'll use two parts of that. The first part is it's like a result I proved with Ziquan 2 years ago, is that for any KOT singularity, the valuation which minimize this function there is actually satisfy that the gradient ring is finally generated. So actually, before this result, I mean, of course, you have to show that the minima exists. That's a result by Howard Bloom, and then we show it's comonomial like longer before, and then eventually we show that this is fine generation. I mean, here I want to remark that the valuation, the comonomial valuation minimize this one is not necessarily divisorial. So the rational rank of that valuation might be larger than 1. So that corresponds to, for instance, the C here is not necessarily in the Q vector. It might be really in R. So in that case, the fine generation is much more complicated, and that's what we call high rank fine generation. But anyway, it's proved. And earlier result, I proved with Chile, maybe 2017, is that we assume this is true. I mean, we assume, so, which now was confirmed, then we know that the x, so if I call this to be, if I call x0 to be the spec of this guy, so if I take this x0 to be the spec of this guy, then the x0 CV, I'll explain what this CV is. If I have this CV0, this I have such singularity, and together with some prescribed vector, then this is K-semistable. And the volume of x is actually the same as the volume of maybe yx0. So there is one single component of x, y, 0. And because this is K-semistable, it's indeed computed by CV. This is on y. And on this side, we know this is computed by v, but this is on x. So basically, this degeneration is actually a volume preserved degeneration. And what's CV here? So CV has to be some real vector. And here, if I write GRVR abstractly, I know it can be written as the gradient of alpha, such that the alpha is in the valuative monoid. However, since we already have a valuation v here, we actually this lambda is inside actually R, right? This is inside R. So this way, actually, I already have a monoid map from a monoid to monoid map from this phi to positive, and of course it extends to a group morphism from Z power to R to R. So that way I got this CV. So the CV is completely canonic determined by V, and then I put that one there. That's K-semistable. So in other words, if I want to understand the value of volume, then I only have to understand the value of the volume for K-semistable Fano cone. So then, if I restate my theorem with Ziquan, then I mean is that so now I assume it's K-semistable Fano cone sorry, I have to move. See, this is a Fano cone, and if I assume the volume of this is is larger than some fixed constant, so I prefixed this constant epsilon, then I will say all such xc is bounded. So you can imagine, I mean, this kind of this boundedness type thing will just imply the fineness of volumes, and then you get the discrete state. So that's what I'm going to discuss next. But as you already heard some of them, historically, there are some without along this line. I think Jin Jun Han, Yu Chen, and Lu Qi. They prove that if X is bounded, but they consider the pair version. I mean, of course, you can state everything here in the pair version, but so they allow that the coefficient of the divider is sometimes DCC, then the volume is DCC. Here because I don't talk about the pair version. You can extend everything to the pair version, but anyway, let me just say the coefficient of the DCC. Then the volume is DCC. So, oh, sorry, yeah, the volume is ACC. Yeah, thank you. So, but the option is here they actually assume that the X is bounded. And then I think Mohaga, Xu, I mean, you heard this yesterday, and then later, Liu, Mohaga, Xu, they prove for the toric case, also maybe the complexity one case. And then Ziquan, I have proved some other cases. I think both this paper and this paper also prove the three-dimensional case of the conjecture. But some part of the Ziquan's argument will be used in my discussion, so I will come back to this later. So Ziquan has some other special cases. So if you want to think about this question, I think that naturally you should start to think about the case that the K is in the Q Rib vector. So then, if I consider this singularity, if I remove the singularity and our quotient, because K now is in Q, so after some multiple it will be in Z, so it will generate a one parameter subgroup. So you just quotient out by the one parameter subgroup generated by K. This will give you a log Fano pair. There will be some divider appear on the boundary, depends on the finite inertial group. But so this is log Fano. So if I want to translate this question into this setting, what does this mean? You have to understand what the volume is. So we know that the X is actually is the cone of, basically you can write it as the cone of V delta for some polarization L. But the L here is proportional to minus Kx minus delta. So minus Kv delta. By the way, this is log Fano comes from the condition that the singularity is KOT. So and the volume then is given by minus Kv minus delta power to n minus 1 times lambda. So if I don't have this lambda, then if I have bound my volume from below and consider all the K-semistable Fano vertices, we know that's bounded. However, this lambda is really a troublemaker. And for a long time, I mean, if you just concentrate on this question, actually, I don't know how to solve directly just on the level of V. You really have to look at the X. And I'll explain this more, but this is the version of C in Q. So if you assume that this is larger than epsilon, and I don't know how to directly prove that this is bounded, such V and delta is bounded. Although from that result we know it's bounded. So then if generally if C in TR, of course you want to, I mean, there are not much way we can directly understand this, because the real vector. So what I want to do is, I want to study some perturbation of this. So this is given by some perturbation. So in other words, I need to understand what happens if I take a look at the neighborhood of C. So let's take an example. I just consider the case that this is a smooth point. This is just a smooth point. And now I consider the C is given by A1, AN. And because I assume they are all in rational numbers, so if I want to get a divisor, actually I have to assume all of them is in natural number, actually positive natural number, let's say. And so let me just call this to be a vector. And then I know the divisor corresponding to this, the valuation, the natural valuation you want to attach to it is of course isomorphic to the weighted projective space given by this one. So let me assume that A1, AN are just kind of general, so let's say co-prime, whatever. So then I also make an assumption to A1 less than AN. Then if I want to calculate the volume, not the normalized volume, but the original volume of this one, that's just going to be the 1 over A1 times AN. So I think anyone can compute this. And the log discrepancy of this is A1 plus AN power to N. So then you say that the normalized volume of VA, that's A1 plus AN power to N. So somehow if the ratio between A1 and AN is bounded, then this volume is bounded. So that means that somehow I perturbate this A in some like a bounded region, then the volume is bounded. So that's very good. However, if you look at the VA itself, is certainly not bounded, right? I mean, if you calculate the volume, if I calculate the downstairs, the quotient, the volume is given by A1 plus AN. But here there is only n minus 1 because this divisor is n minus 1 dimensional variety. So that's why you say that the volume basically of this guy goes to 0. So really you have to time another A1 to AN to make the formula to be correct. So that's actually one of the main issues, how to understand the problem, how to resolve this. So for a while, we just stare at this quotient, and we don't know how to do it. Because if we perturbate a little bit, the quotient, the underlying variety, the quotient variety will change a lot. So we will lose too much information. But it was in one of Ziquan's paper, here are the two papers before our work on this. It's in one of Ziquan's paper, he noticed the following thing, that so instead of consider the quotient, we actually consider the compactification, which is basically a projective cone. So in other words, I add a piece of infinite divisor on X bar. So this is basically just adding the infinite divisor, which is isomorphic to the boundary. So then what's going on here? So if we look at the, so this is, let me call this step 0. Just to find the right global question to attack. That's one of the key points of this. So if I study I look at this pair. So this is the pair I want to look at. So if I restrict to the adjunction along the infinite, this is just isomorphic to kv plus delta v. So in other words, you essentially just adding a quotient on the infinite. That's like a projective cone. And but more importantly, Ziquan noticed that the volume of this projective cone, actually this is very easy to calculate, but somehow you have to notice that this is the same as the volume of the C. So I take the quotient along some direction C, and so I studied so if I want to be more, I mean I only noted it as weight C, but now I'll just replace this notion called C. So in other words, the global volume of your Fano variety, this projective cone, is the volume you put down here. So we have this assumption that this guy is larger than 0. So because the theorem I want to prove is I want to prove the volume has some lower bound. Then here I also have some lower bound. My global volume has a lower bound. And now I want to understand if I perturbate the C to C prime, I want to make some statement there. So the one statement you can easily make it that I can assume that the C prime, the ratio between this guy, so maybe So if I consider the volume of the singularity, and I consider the volume of this C, so this looks like, I perturbate the minimal direction to some C. I require that this is larger than theta, some fixed constant. So this condition is my perturbation condition. So in other words, I want to prove that the singularity is bounded if I have these two conditions together. So in other words, I want to state a stronger version of the theorem. Is that if I consider all the, so now I drop the semi-stable condition. I just consider the Fano cone. But with this condition that the volume of C larger than some constant, and the ratio of volume of the singularity divided by this C, this is larger than some constant. If I just have these two prefixed constant, then all such kind of XC is bounded. So in other words, their setting allow me to perturbate myself and to some rational one and to attach some global questions here. So as I said, this question is already translating this condition on the global variety. Now I need to translate this condition. And Chenyang already, in his paper, he noticed that this condition can be translated to the alpha invariant of the base has a lower bound. So I'll give you an exercise of calculating the alpha for this Witten space. But you really say that this condition will, as long as you A1 to AN, the ratio is bounded. No matter A1 how large, the alpha is bounded from below. So even the volume become very small, but the alpha is bounded. So these are the two conditions now I have, and I want to prove the boundedness result. Okay, now we're in good shape because we are somehow now trying to attack boundedness result. And of course, it's not X bar bounded because I add some unboundedness on the infinite place. But remember, what we want to prove is just the cone itself is bounded, not the infinite cone, not the projective cone. I mean, this is somewhat a strange statement, but you try to apply the general strategy of attacking boundedness for Fano varieties. I mean, you will not get the boundedness of X bar because that's not bounded, but somehow you try to see what kind of result you can get. So, and from there, you try to show that X itself is bounded. So after this preparation, we want to prove the next step. Next step is step 1. I want to show that again, the second condition of alpha is only about V. I want to translate it into a condition of X bar. So I say that if X is not on the V infinity, I look at the local alpha invariant of X for V bar, for X bar, for this pair. So now I look at the local alpha invariant, and I take the minimum of 1. This is larger than the minimum of 1 for alpha X V delta. So how to prove this? Actually, it's rather easy to prove this statement. But this statement basically translates to the fact that if I have an alpha invariant of the base, then I actually have a lower bound of the alpha invariant, at least the local alpha invariant, at least for all the x's which is not on V infinity. So how to prove this? So remember, if I just find the D, which is linear equivalent to some lambda minus kx bar minus V infinity, such that maybe I just write in this way, effective, such that the x bar V infinity plus lambda D is not LC and X. Right? I mean, this is how I want to bound the alpha invariant. So I may assume that, so we may assume V infinity is not contained in the support of D. Because I'm more interested in the localization and the X. So of course I can just forget all the divisor which doesn't pass through X. But now I can just restrict on V infinity. So if I restrict this pair, as I said, this is just give me kV plus delta V plus lambda D restrict on V infinity. But here, because lambda is less than 1, I'm assuming lambda is less than 1, I can just apply Shakarov connecting theorem. I know if this guy is not KLT, then this guy cannot be KLT. Then I just conclude that lambda is larger than alpha V delta V, if this guy is less than 1. So it's just a simple application of the connecting theorem. But we just got this bound. And so remember there was a result by Chenyang Zhuang. He proved that if I consider Fano variety X, and I assume that the alpha X has a lower bound, I assume the volume has a lower bound. Then he actually proved X is bounded with these two conditions. But actually, what he really proved is that the minus mkx is birational when m is larger than m only depends on the alpha and the dimension. So in other words, he proved there is if with these two conditions, there is a uniform m such that this guy is birational, and he used this result to prove, together with the Burkhardt result, to prove the boundedness in this global city. But if we just look at this result, then you immediately realize if I want to prove something birational, I don't have to assume the alpha invariant is bounded away from everywhere. I only need to assume local alpha is bounded away from for some open set of x. Then I'm okay. So in other words, this result immediately already implies this. So I just change my condition. So this condition can be alpha x larger than alpha 0. So in other words, we conclude there exists m such that minus m kx bar plus v infinity. This is birational. This m is only depends on the theta 0 and c and n. So because the alpha, I mean, we know, as I said, from the alpha there, I got an alpha bound here. From alpha bound of this guy, I got an alpha bound of a local on x. And putting all this together, then apply John's result, you get this is birational. It's so-called birationally bounded. Then, so what do you have to do? You just have to keep going, right? Once you have a birational bounded, then you want to say, I want to get the boundings. And what Chenyang Zhuang did was he was just citing some Burkhardt result. Of course, as I said, the x bar is not bounded. That's something of the whole story. So, but what you have to do is you try to look at what Burkhardt was doing and try to translate what's happening in our situation. So step 2. Let me first quote the theorem by Burkhardt in his BAB1 paper. He showed that he assumes 4 conditions. So the first condition is the existence of bounded complement. So this assumption is not just for x. It's actually here we'll later apply for some pair on x delta. But anyway, this existence of bounded complement now is a theorem. That was proved already in his paper. So you don't have to take it as an assumption anymore. And the second condition is minus k is birational. Here all the numbers appear are uniform. So I assume for some uniform m, this is birational. So the third condition is the volume of minus k. The volume of minus k is less than some uniform constant. And the fourth condition is alpha x is larger than some constant. If you have all of these 4 conditions, that will imply x is bounded. So these are like 2-3 pages argument in his paper. So we look at these conditions. The first one, as I said, this is a theorem which always holds. And the second part, the minus mk is right, that's implied by step 1. So step 1 give this. So this condition, I'll explain, it's very easy to get. But this condition is not true, right? We only have the local alpha is bounded from below. We don't have a global. So again, we're not trying to prove x is bounded because that's not true because we add infinite divisor. So somehow we have to look at what's going wrong there and try to fix it. And but let me first explain why this is the third condition. The third condition just follows from some general thing. So now, if we consider the third condition, we are consider the volume in our setting is minus x bar minus v infinity. Right? As I said, this is part of our assumption. This is just the volume of C, then which is given by the volume of x and divided by this theta. Less or equal to given by this theta, because theta there is prefixed. And we just have to have a lower upper bound of this one. But we know, as I said at the beginning, we already know the volume of all singularities with a fixed dimension is bounded by n power 2n, proved by Yucheng and myself. So we already know this. So the volume of, so the third condition is also get. So the only missing thing is the fourth condition, which we know is not true. And because we know boundedness is not true. So
in Zhang's result, what's the condition of x, little x?
I mean, in Zhang's result, there is, he just assumed something global. He didn't assume anything local. But if you track his result, this is true at least for x holds over open, direct open set. So if you just know the local alpha event has a lower bound for direct open set of x, then Zhang's argument can be applied. So, okay. So now we want to so as I said, we need to track Bjerke's proof and understand what's going on there. Maybe. Okay, maybe use this plan.
But then you only need 1 point.
Yeah, I only need 1 point. That's right. Here, I mean, works. I mean, as long as it works for 1 point, it works for direct open set.
So you can take x to be the component.
Yeah, I can take x component. That's right. Yeah. I mean, here, I think the component might have a lower alpha than x, which is not on the infinite divisor. The infinite divisor alpha might really be very bad. So where are we? Okay, so we are here. We're at the end of step 1, and we try to understand the Bjerke's proof in our setting. So what we know is that we know x v infinity, and I add one bounded complement in my picture. And I mean, this is just for some technical reason, but I just want to state the right statement. And from this, we know this is birational bounded by some x plus v infinity by this linear system for some uniform n. And the image of y is in a bounded family because the degree is bounded. And actually, there is a divisor attached there. So basically, we want to say this pair is so-called log birational bounded. So the theta contains. So I misleading call this phi inverse. I call this direction phi. So the theta, the sigma divisor contains the phi inverse of the push forward of v plus gamma. All the divisors I'm interested in on the left-hand side. I mean, it might be contracted for some of them, but at least I remember all the image, and I also remember all the exceptional divisor of this direction. So I consider this pair. I know that this pair is bounded. So, so this is so-called log bilateral bounded if I have this data. But we still want to prove that the x, not x bar, x is bounded. So, as I said, in Berka setting, if you replace this alpha by some alpha 0, but replace this alpha x by this local alpha by global alpha, you really get the boundaries of the entire thing. So what is his argument? So his argument basically, out of all this data, I mean, Berka's argument is that he can construct if you replace this local alpha by global alpha. So if, let me just say, if the global alpha has a lower bound, then you can get another tail which is of this form, such that this is an epsilon log terminal. This epsilon log terminal, and the coefficient d in some finite set. Then you just get boundaries because you can just work on the y side and run MMP to get all the x bar back. So here the crucial point is from log canonic, you have to replace by epsilon log terminal condition. I mean, this kind of boundaries was known for a long time, but the upshot is that you have to replace, you have to get this epsilon log terminal instead of log canonic condition. So what we can get? So in our setting, we can also find the d. But unlike Berka's case, our d is not effective. So there is a d plus minus d minus. This is still on x bar, such that the x bar, it's a v infinity plus d. Sorry, not v infinity, x bar d. If you look at this pair, this is epsilon sub LC. So instead of epsilon LC, now it becomes epsilon sub LC because we have a negative coefficient. But the negative part only supports on V infinity. So in other words, you have a one divisor, you don't have a control. You have a negative coefficient. I mean, of course, in MMP, everybody knows if you have a negative coefficient, that's bad. But for other part, it's fine. So that's what you get after step 2. You basically mimic what Berka did, and then you cook up this thing. So now I can almost finish my argument. So again, I look at this y. I look at the x bar and the d, and so what I can do is I can extract all the divisor over y with such that I replace y by some like terminal model, such that this y, I have this phi map here, and the phi inverse, the extract only contract V infinity. Because all the extension divisor for this pair except because it's an epsilon log terminal. So there are essentially finite many of them. So you can extract all of them, and then on y. Then for adding further divisor, if it appears if it is, let's say, yeah, that's right. If it's exceptional over y, then it has to be exceptional over x bar. So you accept the v infinity. So this way, I conclude that I got a contraction, almost contraction, except over v infinity. If this is a contraction, then I can just run certain MMP to get back x bar from y. But precisely because of this v infinity, I cannot do that. But however, if I consider gamma, so I want to say there exists a big divisor on y such that support A is equal to support of exceptional phi plus phi inverse v infinity. I mean, this might very likely to, sorry, let's phi lower stuff. This might very likely just to be 0. But you somehow you just choose a common model. I choose a common model. I pull back the v infinity. I push forward. That I get some big divisor here. That divisor must support on this one. So I have some big divisor on this y with this, and then I can run MMP for A. You have to argue this to from y get some like a, let's say y bar, and I just want to say that x is isomorphic. So y bar, this is, let's say, the minimum model. And then I got some, like, let's say, ample model. This is the minimum model. This is the ample model. Now I just want to say x is actually isomorphic to y ample minus the, if I call this map to be G lower star A. So in other words, I don't recover my x bar, but I recover x. I recover x by having this Bunyan's model and then removing some divisor. So, and why this is true? I mean, because you just say that under this condition, I know that the h0 of y minus support A is equal to h. So for this, I mean O of this is the same as h0 of OX. Because this part and this part, they are codimension 1 isomorphic. So I remove some divisor here, I remove some divisor here. They are codimension 1 isomorphic. But then you understand that along this MMP, the codimension 1 part, this global section is never changing. So you know that this is the same as 0 y ample minus the support of A. Sorry, this is O. Y ample minus support. So, but of course, X is just take the spec of this. And the part just take because A, there is the ample divisor there. You remove the ample divisor, let's just take the spec of this. Then you are done. So somehow, you only recover the X at the very end. You somehow carry through only the non-bounded part, v infinity, all the way inside the argument. But then at the end of the day, you remove it using the minimum program. And that's a proof. Thank you very much.
Questions?
How do you prove A?
Oh, I mean, basically, the A is, I mean, you think about that, if you pull back this V infinity, you pull back this V infinity, which is ample here, you push forward here, that's big. So then, any divisor, have the same support with A, so it's going to be big. But you have to, like, massage the coefficient such that you can run MMP. But that's just,
Any other questions to Chenyang? Okay, if not, let's thanks Chenyang again.